Hi, my name is Rich Knepper, and this is my presentation on living cyberinfrastructures and scientific research for the International Conference on Infrastructure and Collaboration in E-science and E-humanities. I started thinking about this living cyberinfrastructure idea when it became clear to me that technology and scientific outcomes are very closely linked. And here are some of the previous work that influenced my thinking, and that science becomes a part of the technology that supports it. Cyberinfrastructure consists of systems, storage, networks, software, and people in support of scientific research. And these are very large systems that require significant management and outlays and significant human intervention in order to keep running. On the left side of the slide, I provided the Branscombe pyramid, which describes the distribution of cyber infrastructure. At the top are leadership class machines, followed by large-scale resources, the center supercomputers, all the way down to small-scale resources in the desktop or at home. More frequently these days, that would be your laptop. Now, the top two tiers of this pyramid require a considerable amount of resources in order to keep running, for maintenance, supervision of the networks, adaptation of research software to run on these systems, and so a lot of support, training, and documentation. Advanced cyber infrastructure has traditionally been focused on physics, chemistry, molecular dynamics. These problems require difficult and complex solutions, such as massively parallel code, a need for internode communication. It requires a low latency network to run, and there are a lot of problems making sure that the data is at the system in time for analysis to complete. These systems are shared systems, so they're designed to meet the needs of many researchers working in the same space, but they're also designed to be used in single jobs that may take up the entire capacity of the system at once. These are the very needy. So users have to get used to running on systems with other users and integrate with a queuing cycle or a fair share model. They may have to adapt their code to run on that system, and that may require considerable intervention. And these systems have a life cycle due to funding. They may not be completely useless at the end of 5 years, but there's no money to keep them in maintenance and take care of them. So researchers may find themselves moving from one system to another. These systems are usually based at computational centers, such as those managed by XSEDE, the Open-science grid, the PRACE research infrastructure. The funding for these centers tends to be cyclical, or it may be problem-centric, much like the Open-science grid was largely focused on the discovery of the Higgs boson. There's a limited talent pool of leadership and technical specialists that can support these systems and write the proposals that get these systems funded and create new ones. Now, these centers have a desire to keep existing. So in order to do that, they need to attract new users and provide something useful for new scientific domains that haven't previously run on these servers. So the centers tend to be in cooperative competitive tension. And what that means is, for the most of the time, they're cooperating in order to create something that interoperates with each other in a larger framework. The Open-science grid needs resources that work together, and the same thing with XSEDE. But at certain times, these centers are in competition with each other. They need to show that they're better and more able to handle large projects in order to get that funding that keeps them alive. In our environment, the funding continues to get scarcer, but projects tend to get bigger and bigger as we move towards exascale analyses. And we're still dealing with the same talent pool. Human resources for these projects tends to be fairly limited, and so many of the people who work with these systems come from similar perspectives and have similar histories. So how does living cyber infrastructure differ from standard infrastructure like a microscope? Well, a large-scale system is no longer always used the same way throughout its entire life cycle. It may not also be designed for a single purpose. Computational systems are almost universally configurable depending on what's needed from them. Finally, not every user is using a system like this in the same way. So it's very different from a microscope, which might have been designed for a single purpose and which a researcher will always use the same way throughout their work. What happens because of this difference? Well, there's a bit of inertia of purpose. That means that these systems are designed to meet needs in existing fields that use them a lot, high performance or high energy physics, molecular dynamics. And so these models tend to be the basis for new models. So it's one of these situations where all of the existing working software really only fits the kind of systems that are already out there and the kind of science that's already using them. So this advanced cyber infrastructure in the form of these centers, it has an interest in preserving and replicating itself. Centers want to stay open, people want to stay in jobs, and so the status quo and beyond is the interest of these centers as they develop. There will be scaling issues as the community attempts to scale into the exascale and take on larger and larger analyses. And finally, the centers want to preserve themselves and continue to work. There's still a need for larger, more powerful systems as analyses grow and the needs of the community grow. There are also new analyses, new software appearing all the time. Now, the software doesn't always have an easy time fitting in with existing cyber infrastructure. Some of that is because of the difference in science, and some of that's because of the different models of computational programming. A lot of the existing models for training and documentation are based on fitting smaller communities, and so the centers need to come up with a way to meet larger communities. Finally, even at the top of the Branscombe pyramid, some of the old metrics, like how many floating point operations can a system do, are being discarded. The Blue Water system actually elected not to participate in the top 500 contest on the basis of problems with these metrics. So for a researcher moving from their lab into a large-scale resource, the old way was to just get a new resource, some kind of instrument that would help their science. They would make use of it to get data and they'd publish. Nowadays, it's getting less and less feasible to build single scientist resources. Living cyber infrastructure attempts to provide free capacity to the researcher, but there are other costs involved. These costs are such things as allocation. A researcher has to take part in an allocations process in order to get time to use on a supercomputer. They have to adapt their code. They also have to share the system, and some of the systems have data sharing agreements that require to share their data as well. Finally, these large-scale centers are also looking for attribution so that a scientist would cite this resource that they used to do their science on. So what does this mean? Free cycles mean you can get a lot of work done, but it has to fit into the computational model of existing resources. Not all centers are going to change how they do things just to fit your particular needs. Doing science on these systems requires that you might have to attribute, you might have to work with programmers and application specialists on the system in order to make your software work, and you might have to participate in some survey or some other feedback into the center that allows them to understand how things work. At the end of this, living cyber infrastructure begins to claim a part of the scientific process. If you couldn't get the research done without a supercomputer, how else would you do it? It's not like the old days where you might think of the microscope as a piece of furniture rather than an integral part of the research process. So are new methods such as big data analytics a way of fitting some existing problems into these highly computational models for social science? What would cyber infrastructure that was designed specifically for new domains, not previously used, look like? And what are the arrangements that are possible between traditional science and the living cyber infrastructure? So for computational systems are adapting to non-traditional domains, and that includes providing more memory, providing specific algorithms. Furthermore, there's calls within that community to provide more software that fits better to these large-scale systems. Cyber infrastructure for new disciplines might look like a networked opera, as presented in the image on the left, or a light tower that's computer-controlled, or finally the Center for Computational Social Sciences at Stanford. So what's the relationship between living cyber infrastructure and science? Firstly, there's an explicit use for allocation. Scientists have to get an allocation and justify the science that's running on the system. It cuts down on some of the experimentation that may take place early on in a project. Projects need to be collaborative between the infrastructure and the research. So, for example, the LHC and the Open-science grid. Finally, cooperative arrangements may arise in between research and projects to provide resources in return for attribution, optimization of software, and maybe finally taking part in the research process itself. So, what does this mean for research? There's new demands for researchers who want to make use of this capability. They have to participate in the process. There's a search for new models for sustainability of research centers. The collaboration and compete cycle is not a permanent cycle, and things may change as funding changes. And finally, cyber infrastructure may be an integral part of scientific discovery such that it becomes a participant in the scientific process. Thank you very much. Hope to see you at the conference.